Okay, so we've got these two particles that are stuck together. Let me just pull up a blank screen here. I can run. Okay, so I have a negative ion, let's say, chlorine ion. Dang. And I have a positive ion, the sodium ion. And they're stuck together, and the dissolving process needs to pull these things apart, okay? There's got to be some kind of a force acting on these things that pulls them apart, and then once it pulls them apart, it keeps them separate, okay? So there's two kind of things going on here. I've got to pull these things apart, and then I've got to keep them separate once they're pulled apart. And it would hopefully make sense that the only thing that can really work in this scenario is something that has electrical charge itself, okay? If you don't have a thing, you should yell at me and say, Marshall, I need a... I'll let you copy. Does anyone else need one? Okay, so it should make sense that something that has an electrical charge could pull these things apart if I've got enough electrical charge. And what we've said is that I've got these water molecules that are polar, and one end of the water molecule's got some negative charge on it, and the other end of the water molecule has positive charge on it. So hopefully it would make sense that, let's make this a little bigger. Hopefully it would make sense that the water molecule could do this. So now I've got come on. The more positive end tugging on the chlorine, and it's like these water molecules exert little tractor beams. Now, the negative charge here is not nearly as strong as the charge holding these two things together. So I'm going to need a bunch of these. I'm going to need a bunch of these snaking out their little tractor beams and pulling on this ion here. And I'm going to need a bunch of these with their positive ends. Snaking out their little tractor beams. Okay, and eventually I'm going to get enough of these water particles that they're going to be able to cause these to be pulled apart. Okay, and that's what the dissolving process is all about. I've got these water molecules that have partial negative or positive charges latching onto something that's positive here, or the positive parts latching onto something that's negative. Let me ask you another question. If I have, let's say, magnesium chloride, or no, let's say magnesium oxide. Oops. But magnesium is 2 plus and oxygen is 2 minus. Which of these do you think is going to take more force to pull apart? The sodium chloride, which has one charge, or the magnesium oxides, which have two charges? Yeah, it's going to take more force to pull these apart because I've got more electrical force of attraction holding these things together. So if I'm talking about ionic compounds, hopefully it makes sense that things that have more than one charge are going to be more difficult to dissolve than things that just have one charge. Okay? So this is kind of the idea of what we're talking about here. So knowing that water has this polarity, can you think of a reason that might cause molecules or ions that are part of a solid portion of a compound to pull away from that solid portion? It's usually a crystal. Recall the basic theme is of an ionic. Recall that the basic theme of an ionic solid is that there are alternating positive and negative ions that are held together in irregular repeating structures. Anybody remember what we called this structure of positive and negative charges in kind of a three-dimensional crystal structure? What do we call this three-dimensional structures? Anybody remember?
Hard to draw.
Huh?
Hard to draw.
It is hard to draw. Remember the term lattice?
No.
Okay, we called this a lattice. Okay, garden lattice is like that little fence, kind of the little fence, you know, that looks like this and the vines crawl all over it. That's a garden lattice. So a lattice is kind of a regular structure, and this crystal forms that regular three-dimensional structure. So in the dissolving process, as large number of polar water molecules approach the crystal, the negative, and which is the negative portion, the oxygen or the hydrogen? The oxygen's the negative portion, right? The oxygen portion of the molecule is attracted to the positive ion, and the positive end, or the hydrogen, end is attracted toward the negative ion. Okay? And if the negative portions of enough water molecules approach the sodium ion, they may tug the ion off the surface of the crystal, after which it becomes surrounded by negative portions of multiple water molecules. Likewise, if the positive portions of enough water molecules approach a chloride ion, they may tug the ion off the surface, and it also becomes surrounded by multiple water molecules. Okay, you have a slightly different diagram in your notes, but what's going to happen is that I've got these gray colored balls here are going to be sodium ions, and the green ones are going to be chloride ions. And notice that on the negative ones here, for example, right there, I've got this water molecule sitting on it, and it's the hydrogen ends that are attaching themselves or pulling on that negative ion. And on the positive ion right here, I've got the negative part of the water molecule pulling on it. And what happens is that ultimately, once I pull these things off of the crystal into the water, they become surrounded by water molecules. You can see these are all surrounded by water molecules now, and that prevents them from reattaching back to each other. Okay, that prevents them from reattaching back to each other. So we have one other idea or thought to talk about then related to this. Come on, scrunch back down. It's not that far. I must not have enough friction with my fingerprints or something. Come on. Why are you doing this? Okay, so the process continues until either all the ionic compound is dissolved and uniformly dispersed, or at some point, maybe I don't have enough water molecules present to generate enough force to pull more ions away from the solid, and at that point, the solution is said to be saturated. Do you have a blank there?
Yeah.
Okay, so that's the point at which the solution is saturated. Okay? So what do you think determines whether or not water molecules can pull ions away from the ionic solid? We already sort of approached this. What's going to determine how successful the water molecules are at pulling these ions away from the crystal? Yeah.
How strong it is?
How strong what is?
The positive and negative from the water molecules.
Okay. Let's put that in a little different perspective. Let's say how strong the force of attraction between the ions is. Okay? How strong is the attraction between the ions? The stronger the attraction between the ions, the less successful the water molecules are going to be at pulling them away from the crystals. How strong the force of attraction between the ions is. And so the is referring to the force of attraction, not the ions. Okay, and did I stop there or did I want that last question too? Nope, I want that. Okay, so you have some space here, and I'm not sure why my lines aren't showing up. Actually, the solution process is a competition between three different forces of attraction. Okay? Maybe it makes sense that the water molecules might prefer to attach onto themselves than onto the ions. Okay, so we've got three competing forces that we're going to talk about here. The force of attraction between the ions, and that's the most important one. And let's just draw a little sodium chloride molecule there. So the force of attraction at that point right here, right? That force of attraction is going to be the main one. Okay? Number two, the force of attraction between the water molecule and the ion. And so let's just draw a little okay, so this force of attraction right here, and this force of attraction right here, represented by these dotted lines. And recognize that this force of attraction is a lot stronger than this force of attraction is. And then our third force of attraction, it may be that the water molecules would rather attract each other than the ions. So we've got these three competing forces of attraction. Force of attraction between the ions, the force of attraction between the water molecule and the ions, and the force of attraction between water molecules. Okay, and these are not easy to predict, okay? There's no way for us, especially in a high school class, to predict which one of these things are going to be the most important in any given circumstance. But they all work together to determine whether something will dissolve or not and how much of it will dissolve. Remember, each of these different substances dissolves a different amount in water, and it's these forces that are going to determine that.
Mr. Marshall?
Yeah.
If you were to have the force of attraction between the sodium chloride and the water, by you stirring, would that create more force, or would that just make it the same time frame before combines together?
So how vigorously you stir the solution will shorten the length of time that you get to saturation, but it's not going to change anything about how much will ultimately dissolve, because the amount of force that these water particles can attract of these ions is going to be determined by how many water particles you have in your sample. So if I have 100 grams of water or 100 milliliters of water, that represents a certain amount of force for those sodium chloride particles, and it's always going to be that same amount of force unless I heat it up. You know, if I add temperature, then that's going to make it so that the bond between these is weaker. Yeah, Garrett, go ahead.
Is the third force the reason why when you heat it up, it makes it faster because it's going to speed up the water molecules and make it less likely for them to bond and find some liquid for the gas?
Okay, so the main thing that's going to make the dissolving occur faster is the fact that the heat's going to make the bond between the sodium chloride weaker. Okay, now certainly all these particles are also going to start moving faster. Okay, and it may be that in some way you're disrupting these hydrogen bonds between water, and that makes them more available to pull on the sodium chloride. And it sounds like that's what you were kind of asking. So that's probably a factor too. I guess I've never thought about it to that degree. That's a great question. So my answer to that would be probably. Yeah, Kristen.
So kind of along with that, wouldn't that sense the molecules are moving around more? Wouldn't that also like raise the odds of H2O coming in the
Hold on. What?
Can you go to your office phone real quick?
Sure.
Where is it?
It's right here. So go ahead.
So since it's heated up and all the molecules are more active, that also make it more likely that the water will, a single molecule of water would come within range of the sodium chloride like area.
Would it make it more likely that the forces of attraction would develop in the first place because it would make it more likely that a water molecule would get closer to the hydrogen or the sodium chloride?
Close enough. and move away in time for another one.
That's possible too, but recognize when I heat the water particles up, it's also going to make this hydrogen bond between these guys weaker because the water particles. So there's going to be some positive and some negative things that go on in there. And that's why it makes it so difficult to actually create a model for this and be able to predict with certainty what everything is going to do. In all likelihood, in most circumstances, it's going to be the strength of this bond here that determines, for the most part, what can be dissolved. And that's kind of what we see when we look at ionic substances that have more charges. They are more difficult to dissolve. So that's the main factor. But all of these other things are going to play into it a little bit. But compared to how much this factor is, it's not as much. But you still need to be aware of these things. Other questions? These are excellent, excellent questions. So what I've said there, I'm having trouble moving my text. So what I've said there then is, while water is highly polar and effective in dissolving the ionic substances, the attractive force between some ions is so great that these substances won't dissolve, or only a very little. Your book gives examples, except you don't have a book, but lead sulfide, we only dissolve 10 to the negative 14th grams per 100 grams, should be 100 grams of water. And then finally a question, when ions of a substance like sodium chloride dissolve in water and disperse uniformly throughout the solution, why do the individual sodium and chloride ions retain the physical and chemical properties of the salt instead of reverting back to their individual chemical properties as sodium and chlorine? Any thoughts about that?
I guess they still retain their positive and negative charges, so that probably plays into that a lot. And it's because they're still ready to go back together, like maybe with a different chlorine molecule.
Okay, so when I've transferred that electron to chlorine and it's now a -1 charge, or when I've lost that single electron from sodium and it's now a positive charge, the change of the electron structure is what gave it those properties in the first place. And that hasn't changed, right? Those sodiums and chlorines are still going to have the same electron structure when they're separated as they do when they're in a crystal. So there's not going to be any change. So what I would say there is that the electron configuration of sodium and chloride ions is not altered by dissolving. So for all intents and purposes, is this a physical change or a chemical change?
Physical.
It's a physical change, right? Because we don't alter the chemical structure. Okay, so we want to start learning about how to create solutions. And actually, I'm going to stop this. Make sure Gary gets the sheets.